There's some things that we've already talked about on the airplane and a few cautionary things. There are a lot more cautionary things that will be discussed later on. But right now, we'll just go on and begin sort of outlining how the course is going to go. I began talking about the instrument panel, and I will continue doing that. But right now, I just want to let you know that we're going to be talking about this particular Mooney M20, and it is probably going to be the plane that we talk about the most. This particular plane here, this one. As you can see, the top cowling has been removed, and the baggage door, I shouldn't say baggage door, but the tail cone electrical access back there has been removed at the tail end of the airplane. By the way, I might as well start throwing some terms out at you. They tell me that the best way for anybody to learn anything is constant repetition. That top cowling is spelled C-O-W-L. The tail cone, or the tail area of the airplane here, is called the empennage. Empennage, E-M-P-E-N-N-A-G-E. I guess it's a French word meaning tail and tail feathers. The M20K model is the one that we're talking about, the Mooney. It is a low wing aircraft, fixed wing aircraft. It does have retractable landing gear, and it has a controllable propeller, a constant speed propeller. This is more advanced than a typical airplane would be when you are learning how to fly. But I figured that we'll try to get as much information as we can in these videos to help you determine or decide where you're going to end up in aviation. I also have the top cowling removed here because we want to, when we go into the engine section, I want to show you the components of the engine. This aircraft, again, is a fixed wing, single engine aircraft with retractable landing gear and a constant speed propeller. This is called a complex aircraft rather than a fixed pitch propeller. The propeller on this aircraft has a variable pitch. It can vary the bite, or it varies the bite of the blades in order to make sure that the engine is running at its most efficient power production setting and RPM to give you the most efficient amount of thrust, or to give you the most thrust for that power setting. It is called a constant speed propeller because once the speed of the engine is set, whether the aircraft climbs or begins to descend, the blade pitch adjusts automatically and maintains the engine at a constant RPM. It also will maintain that engine at a constant RPM no matter how much gas you add or subtract from the engine beyond or up to a certain limit on the addition or subtraction of power from the engine. If you pull back power on the engine, then the blades, in order to maintain a constant speed, would have to decrease their bite, or vice versa. If you wanted to increase power or thrust in order to maintain a constant speed, the propellers would, or propeller blades, would increase their bite to give more thrust or higher power for that higher power setting. Again, we're going to concentrate on this particular aircraft during most of this discussion. This will only be a discussion and initial familiarization with the components of this particular aircraft. We left off in the last video and we began to talk about the purpose of this outside air temperature gauge. The outside air temperature we talked about could get the airplane into trouble if you were to fly into visible moisture like clouds and the outside air temperature was cold enough to freeze. We said that if you knew that the aircraft or the air was cold enough to freeze, that you wouldn't want to fly into visible moisture. If you did not have an aircraft that was certified to fly into known icing. It's pretty obvious what would happen if you were going to fly into a cloud where the air temperature is freezing or near freezing. You'd end up with a load of ice on the aircraft. You might end up blind. So the OAT, outside air temperature gauge, is there for that reason, to keep you away from outside problems or problems with icing. Another reason for this outside air temperature gauge is to compute aircraft performance. Engine power being developed in the cylinders, or the amount of air that is ingested or induced or drawn into the cylinders through the induction system. That amount of air actually changes, or the weight of the air changes. The mass of the air changes based on outside air temperature, or the temperature of that air. If you wanted to compute a amount of true airspeed or rate of climb to arrive at an initial altitude, or a assigned climb to and maintain altitude, an altitude that the air traffic controllers told you to climb to, that is one that you may have filed in your flight plan, or you may have just been assigned to it to get over traffic or over obstacles or over weather. And if you wanted to know if you were going to arrive at that assigned altitude, or if you even could arrive at it, then you might want to know what the outside air temperature is, so that you can compute the horsepower for that climb or for that altitude change. Again, this one is called the OAT gauge. The indications are in Fahrenheit based on whether or not you push the mode select button. Right now we're reading 14.1 volts. Again, to review, E is typically talking about EMF, or electrical motive force, which is also called voltage. Right now it's set to indicate volts. There is a Fahrenheit OAT indication and a Celsius OAT indication. That is possible by selecting with the mode select button. We'll continue the discussion of these instruments, and where the OAT probe is located on this particular airplane. We'll talk about some other airplanes and other sensors as we go along, but want to review and talk about things several times in order to get the repetition in. This particular gauge, and I'm going to take a look at the camera to make sure I'm getting the screen fully, like I did not get before. Looks like I am getting it fully. This particular gauge is the airspeed indicator, and it is typically located on the top left side of the instrument panel, right in front of the pilot's face. This is a gauge that tends to dominate pilots' thinking. This one and the next gauge, the attitude indicator, seem to be the ones that attract the most attention for VFR pilots anyway. And they both, this gauge and the next gauge, the attitude indicator, this airspeed indicator, if the pilot becomes so dependent on the airspeed indicator that, and has trained to depend on it to the extent that he loses the feel of his aircraft, anything can fail. And if this gauge fails, then the pilot without the feel of his aircraft would tend to, well, be confused about what his aircraft is really trying to tell him. And this has happened with several airliners, where the captains of large airliners, I think it was even a 380, it might have been an A320, but it was a large airliner, and the pilots couldn't feel what the aircraft is doing, or they didn't intend or they didn't try to feel what the aircraft is doing. And although their airspeed indications and their air data indications said that this aircraft was flying slower than it should be, they didn't pay attention to it. Anyway, let's talk about this particular gauge. The airspeed indicator here has quite a few range markings, is what we call them, and they're placed on the gauge in different colors, and we need to know these colors and the indications that this gauge will give you. Components of the gauge are the knob down bottom left here. When you turn that knob, what you're going to be turning is the inside white scales or cards behind the front face of this gauge. You turn the knob and both these white scales will move. We'll talk about the arcs and what they're for. And right now the gauge typically is reading 0. There is no airspeed. The aircraft is not moving. The sensor that is plumbed, connected to this gauge, is called the pitot tube, P-I-T-O-T. And I'll show you where it's located on the airplane or eventually. You'll get very familiar with it. Evidently that is also a French word, P-I-T-O-T. We would say PDOT, but it's pronounced pitot, although you will hear Americans say PDOT. And basically what it is a straw held rigidly facing forward. And if the airplane, as the airplane goes faster and faster, the wind is rammed into that straw and causes the needle on this gauge to move. As the airplane is taxiing or running down the runway and the gauge reaches this location, this particular position on this gauge, this is the stall speed, and sometimes people have used it as a takeoff speed for this aircraft or an aircraft. Might have the same color range markings, but they will be at different locations or different speeds for a different aircraft. But this white arc is a flap operating range arc. I have to get a little training aid that I brought with me to talk about where these control surfaces are. This is a P-51 Mustang, a little model I got from a hobby store for this purpose. Anyway, these are the flaps. Both these items are right here. These are ailerons outboard of the flaps on each wing, but flaps are for the purpose of slowing the aircraft and increasing lift. Up to a certain point, you'll get more lift. When you extend the flaps come down together. Both flaps, left and right flap, will come down, and they act as a form of speed brake, but they also increase lift as they're first moving. But beyond a certain extension, typically 20 degrees of flap extension, they become more of a drag-inducing device, slowing the aircraft down quite a bit. You don't want to extend these flaps unless you are in this white arc, the flap operating range. If you extend them beyond this high end of the flap operating range, you may do damage, structural damage to the flaps or hinges or actuating mechanisms in the aircraft. The low end of this flap operating range is the stall speed of the aircraft with flaps fully extended and landing gear fully extended. Both landing gear, both wheels, and the tail wheel on this tail wheel aircraft would be extended, and the flaps would be fully extended, and the aircraft would continue to fly down to this speed, approximately 56, 57 knots is what this gauge is indicating. Knots per hour and not miles per hour. And that is nautical miles per hour. A nautical mile is a little bigger than a statute mile. This aircraft, if it were indicating 100 knots, would probably be flying if you were going in miles per hour, slightly above that at about 110 miles per hour. And we'll look at those conversions later as we get more deeply into the course. Again, the white arc is the flap operating range. Do not extend the flaps when you're going faster than the top end of that white arc. And the bottom end of that same white arc is the stall speed of the aircraft with flaps fully extended and landing gear fully extended. That means the aircraft will stop flying if you go slower than that with the airspeed indicator. The green arc, which is the concurrently or co-located arc, is the normal operating speed range of the aircraft with flaps retracted. And it extends from, what's that, about 62 knots, and it goes all the way up to the bottom of the yellow arc. At about 177 knots is a normal operating range of this particular aircraft airspeed indicator. The lower end of that green arc is the stall speed with the flaps retracted, flaps and landing gear retracted. They say this is the stall dirty speed, flaps and landing gear extended, and this is the stall speed with the flaps and landing gear retracted. That green arc normal operating range, speed range of this airspeed indicator and of this airspeed, this aircraft, is typically a range where you won't hurt the aircraft if you yank on controls full travel. And I have not gone to the POH, Pilot Operating Handbook, to discuss maneuvering speed. They really should indicate a mark maneuvering speed on the aircraft, on this airspeed indicator, like they do these arcs here. Maneuvering speed is a speed where you can yank the controls if you were flying and let's say you were in a dogfight, huh? Or if you just wanted to do an accelerated stall during normal pilot training. An accelerated stall is basically yanking on the flight controls, usually in a bank, usually in a turn, and you're pulling the nose up. That means you have pulled back on the control yoke or stick, and you're trying to climb. In this case, you have a wing low, so climbing is moving in this direction rather than up, although you can climb like that. But if you pull back on the control yoke hard, full travel, to make the aircraft stop flying, meaning that you begin to fall this way, you begin to a stall, and that has nothing to do with talking about if the engine is developing power or running smoothly or full power or whatever else. Stalling does not have to do with the engine. We're talking about the wings stopping flying. They don't fly anymore. An accelerated stall means you are going fast before you make the bank and yank on the control and you cause the aircraft to fall in the direction you were already traveling. To recover from any stall, you would push the nose down or allow that wind to begin to flow again on top of the wing. Anyway, maneuvering speed is typically the airspeed at which you can do that full yank, full travel of the flight controls without doing any damage to the airframe of the aircraft. Again, these are the flaps. They come down together. Takeoff flaps is usually less than 20 degrees of flap extension. It adds a lot of lift to the aircraft so it can take off at a shorter takeoff roll distance than if all flaps were retracted. You can take off with flaps fully retracted, or you can take off with flaps extended to a takeoff position. Beyond that takeoff position, if the flaps were fully extended, they become speed brakes and you might never get off the ground. Or if you did, you'd only stay in ground effect and not be able to climb out of the airport area. You might run into a building or something if you try taking off with more than takeoff flaps. Again, the white arc is the flap operating range. The bottom end of the white arc is the stall speed with flaps fully extended, coming in for a landing typically. The top end of that white arc is do not extend flap speed. The green arc, bottom end, is flaps and landing gear retracted or stall speed clean. And the white again is stall speed dirty. Green is normal operating range of the aircraft. Maneuvering speed is typically lower than the top end of the green arc. It might be somewhere around 150 knots for this aircraft, but know what your maneuvering speed if you're going to fly that airplane. And again, the next range of the airspeed indicator is the caution range. And this is a speed at which the aircraft really should not operate in unless the air is smooth. This is okay to fly in turbulent air. Maneuvering speed is typically up at near the top end of the green arc. You can fly over bumps down in turbulent air if you're below that maneuvering speed. But if you go above that maneuvering speed or the normal operation speed, the air has to be smooth or else you could do damage to the airframe. Yellow range, caution range, smooth air operations only, and the red line here is VNE, or velocity never exceed speed. Don't go any faster than that speed. During normal cruise, chances are you won't be able to approach the red line speed. At a set altitude and a set power setting, even at maximum power setting, typical airplanes do not approach that red line speed. The only way you can get the airspeed that fast is to be in a dive, typically. I'm not going to say all aircraft don't have enough power to reach red line in a normal straight and level flight attitude, but typically you'll have to be in a dive to get to that speed. It's legal to go to that speed, but don't exceed it, especially don't exceed it. The two white cards behind the normal face of this airspeed indicator are cards that are for the purpose of determining what your true airspeed is of this aircraft. Although we haven't really had a chance to talk about the different types of speeds, I will begin to mention them because repetition is a good thing. We have indicated airspeed, which is what is indicated on the gauge itself. We have true airspeed, which is actually the speed of the aircraft going through the air, going through the actual air mass that you're in. And it won't be the same as indicated airspeed without a temperature and altitude correction for that aircraft or for the air mass that you're flying in. Another airspeed is called calibrated airspeed. Calibrated airspeed is what they say it's indicated airspeed corrected for position error, meaning that if the pitot tube, which is the probe that sticks forward in the aircraft, in the airstream, is at such a distance from the airspeed indicator, and the long tube coming up to the airspeed indicator from that pitot tube causes a certain amount of pressure drop, air pressure drop, then that position error is what they're naming calibrated airspeed, or they say the definition of calibrated airspeed is indicated airspeed corrected for position error. That line droppage or whatever other types of errors that might be induced into the actual indication on the gauge. Then we also have ground speed. That's the actual speed over the ground, no matter what the wind is doing, no matter what the indicator is doing. So again, we have indicated airspeed, we have calibrated airspeed, which is the definition of which is indicated airspeed corrected for a position error. We have true airspeed, which is the speed of the aircraft actually going through that particular air mass. And we have ground speed. If the air mass is moving fast enough, you might be indicating a good high indicated airspeed. But if you're flying into a severe headwind, like into a jet stream, and it's blowing against the aircraft, holding the aircraft back, then ground speed could be as low as 40 miles per hour, 40 knots. If we're talking about a gauge that is indicating in knots. So you can indicate a very high indicated airspeed, but you are making very little progress over the ground if you're flying into a headwind. Flying into a tailwind of a high magnitude, like we were just discussing, jet stream gets over 100 knots. A jet stream can blow pretty hard and give you a very high ground speed. So again, indicated airspeed, calibrated airspeed, which is indicated airspeed corrected for position error. True airspeed is indicated airspeed corrected for altitude and for temperature. And ground speed. Now we'll talk a little about true airspeed right now. These white cards again are positioned by the knob at bottom left here. This indicated, or this window here, has a pressure altitude label here for these numbers, and it also has a temperature in Celsius scale indicated by these numbers. Determining the true airspeed of this aircraft going through the air is not typically something that most pilots would really waste time to do. They're more concerned about the ground speed and fuel consumption and things like that. But true airspeed on this gauge can be determined by rotating the pressure altitude card to the actual pressure altitude, and that is determined typically by setting your altimeter, and we'll get to that later when we talk about altimeter. But it's typically determined by either you can talk to flight service station or flight service, or the FSS flight service station that the FAA or private contractors now run. You can call them on the radio, typically at 122.0, although they have several frequencies that you can use. But you can call them on the radio and ask them for a altimeter setting for a particular location that you're flying over or flying to. And you can set that altimeter to that altimeter setting to get a more accurate altitude, indicated altitude. But if you wanted to know the pressure altitude at your particular altitude, then you would set that 29.92 inches of mercury in the altitude Colesman window, altimeter Colesman window, to determine if you're flying at 8,000 feet pressure altitude, and if it's, say, 20 degrees Celsius on the OAT gauge, if you hit Celsius, then matching the 8,000 feet at the 20 degrees Celsius indicator, matching the 8,000 with a 20 degree Celsius indication, that's pretty hot actually, will give you a indicated true airspeed that you would read on this scale based on temperature and altitude correction. That'll be your indicated airspeed with temperature and altitude, pressure altitude corrections. All right, that's one review. White arc, flap operating range. Green arc, normal airspeed, normal operation range. Yellow, smooth air, caution range. Red line, don't go faster than that. Velocity never exceed, or V&E. Bottom end of white, flaps, gear down, stall speed, dirty. Bottom of green arc, flaps and gear up, stall speed, clean of this aircraft. Stops flying at the bottom of those arcs. True airspeed correction windows, indicating in knots and indicated airspeed. We have 4 different types of airspeeds: indicated, calibrated, true airspeed, and ground speed, actual speed over the ground. Next gauge we'll talk about is the attitude indicator. Sometimes this one is called a flight director because it does direct the flight of the aircraft if they're flying in auto flight mode or in a flight director function mode. The attitude indicator is also called the artificial horizon because that's what it does. It gives you an artificial horizon. A blue sky here and a brown or red color for the base of it, or the below the horizon indication or colors indicates the ground or the earth. The aircraft indicator or aircraft pictorial display here is the yellow triangle. This attitude indicator, and the word attitude indicator is the most common term for this indicator on small aircraft like we're talking about. It's also called, again, the flight director. Sometimes it's called the ADI. So most times it's called artificial horizon, but attitude indicator is probably used 50-50 with artificial horizon in small aircraft. Right now it shows an indication, and because the aircraft is not running, this indication is not accurate. And this bar here would typically be matched with the horizon bar, and that is a 90-degree of bank bar on the index here. This is a gyroscopic instrument. It uses pneumatics or a vacuum pump or sometimes a pressure pump even to spin the gyroscope that's in this gauge. This particular attitude indicator does have the characteristics of a flight director. You don't see the V bars that are coming down or would come down into visible display here, one from each side. If you had flight director mode or altitude or any other mode selected where those V bars could give you commands, those V bars are also called command bars. Those command bars would tell the pilot if he wanted to climb to X altitude that was programmed into the flight director system or float or programmed into the autopilot system to climb to an altitude. The V bars would come down to a certain position on the gauge, and my hand is supposed to be indicating the V bars that came down. If he wanted to go to a higher altitude, the V bars would come down to an altitude above where he is level at, and then the pilot would follow that command of those V bars and tuck this V into the V of those 2 bars and hold that